Well, this is going to be about primitive roots. That's chapter 7 from the book. This is all about study of reduced residue system. So to begin with, let me recall what we already learned about reduced residue systems. So that is a recall. Reduced residue system we start with a positive integer, a little bit bigger than 1, and we had definition 4-4 in the book. What is a reduced residue system? This was a set of integers R1 up to Rs of integers is called a reduced residue system. Modulo M if the following conditions are satisfied. First, all these integers are relatively prime to m. The greatest common divisor of any one of them and m is 1. Second, they are all distinct modulo m. Ri is not congruent to Rj modulo m whenever I is different from j. And the third requirement is that every integer which is relatively prime to m has a representative among them. So for each integer n such that the greatest common divisor of n and m is 1, there is Ri which is congruent to n modulo n. There is a difference between complete residue system and reduced residue system. So in reduced residue system, they are all relatively prime to m, and it contains representatives only for those integers which are also relatively prime to M. Complete residue systems have all representatives modulo M. It is actually more convenient to speak about not a system of numbers, but a system of modulo M residue classes. The book uses integers. We discussed equivalence classes. You remember that being congruent modulo M is an equivalence relation, and we have all integers split into classes, equivalence classes. It is cleaner to speak in the language of equivalence classes, but because the book uses another language, I will use both interchangeably, simultaneously. So this is the definition of a reduced residue system. We know that every reduced residue system modulo M has the same amount of elements, the same size, and this was a notation phi of M, the Euler phi function, is the size of any reduced residue system modulo M. Specifically, it is sometimes convenient to choose as a reduced residue system if we want to choose speak about not classes modulo M, but just integers as the book does. It may be convenient to choose this one. This was theorem 4-5 in the book. The set of integers, all bigger than 0 or smaller than M, such that the greatest common divisor of R and M is 1. All positive integers smaller than M and relatively prime to M. This is a reduced residue system. Modulo M. Modulo M. If you prefer the language of equivalence classes, this is the set of representatives for all equivalence classes, one from every class. Equivalence classes in a reduced residue system modulo M. We start with an observation about a possible operation with elements of a reduced residue system. While we cannot add elements of a reduced residue system. I will abbreviate RRS for a reduced residue system. It takes time to write too many words every time. So we cannot add the elements, but we can multiply them. What does it mean? Oh, what does it mean we cannot add them? I mean that modulo let m be 7. Modulo 7, 3 and 4 elements of a reduced residue system, mod 7. But taken naively, 3 plus 4 is 7, is not. That is because both 3 and 4 are relatively prime to 7, while 7 itself is not relatively prime to 7. However, we can multiply them. Let us check that general setting modulo m, whatever m is, we have that the greatest common divisor of one element, R1 and m, is 1. At the same time, the greatest common divisor of another element, R2 and m, is also 1. These two imply that the greatest common divisor of R1 times R2 and m is 1. Indeed, that's a very easy application of the fundamental theorem of arithmetic. R1 shares no prime factors with m, same about R2, therefore same about their product. Every prime factor in the product is a prime factor of either R1 or R2. So there are no prime factors in common between this product and m. That means that if R1 and R2 are two elements of a reduced residue system modulo m, then R1, R2 is a representative of another element of reduced residue system modulo m. It may be one of them, may be different, most probably different, but still it is an element of the same reduced residue system. The difference is drastic. Here, the sum is not an element of the reduced residue system, the product is. Here I rather think about classes, not numbers, because the number R1, R2 may not be in the reduced residue system, but there must be a number, must be because for each integer n, there exists a representative, so there must be a representative for this number in the reduced residue system, simply because this number, if you think about the product of two numbers as a number, is relatively prime to m. Since we can multiply elements of reduced residue system, we can take powers. And we can reformulate this way, or just recall Euler's theorem. So we can not only multiplying some element by itself many times, we produce the power of this element. We have theorem 5-2, Euler, that if the greatest common divisor of A and M is 1, then A taken to the power phi of M is congruent to 1 modulo M. Now, in other words, we now can say that every element of reduced residue system raised to power phi of M is this element of reduced residue system, the element whose representative is 1. In this connection, we can consider some element of reduced residue system and all powers. So let A be an element of reduced residue system modulo M. Consider the powers. So 1 is definitely A to the 0. And after that, we can multiply by A. A to the power 1, A squared, A cubed, and so further. To the 4, to the 5, whatever. At the moment, we are guaranteed to get 1 again, 1 modulo M. We think about this not really as numbers, but as representative of classes modulo M. So at some moment, we will get A to the power phi of M, which is same thing as 1. And after that, we continue doing the same thing, multiply by A at every time, at every step. Next one is going to be this 1 times A, which is again A squared, and again, what we see that this sequence A, 1, A squared, A cubed, cycles. So at least after a while we get to 1 again and begin same sequence, same finite number of elements again. By the way, if A is not in reduced residue system, this will not happen. So this is a remark. If the greatest common divisor, well, let me write it this way, the greatest common divisor of A and M is bigger than 1, I wanted, call it D, the greatest common divisor of A and M bigger than 1, then the situation is going to be quite different. Or indeed, we will never return to 1 again. So, A to the power B is congruent to 1 mod M, then cannot happen. For any integer b bigger than 0. A to the 0 is 1, but after that it never returns to 1 again. Indeed, that is simply because what does it mean? What never happens? Let us briefly recall the proof. This congruence means that M divides, so this is because M divides the difference A to the B minus 1 so this cannot happen because M does not divide this difference. That is because our D divides M but does not divide D divides M, but D does not divide A to the B minus 1 unless B is 0 and A to the B is 1, 1 minus 1 is 0, but we assumed B is positive. So, because D divides A, and therefore D divides A to the B, therefore D does not divide A to the B minus 1. So D divides M does not divide A to the B minus 1, means M cannot divide A to the B minus 1. Roughly speaking, these D will not cancel out. That is exactly what theorem 7-1 says. In order that A to the B is congruent to 1 mod M, for some integer b, positive integer b, it is necessary and sufficient that the greatest common divisor of A and M is 1. And it is sufficient because such B is simply phi of M, and this happens for some integer, for phi of M, this happens. A to the phi of M is 1 by Euler's theorem. And this remark, this discussion, showed that if this greatest common divisor is not 1, is bigger than 1, this was D, this cannot happen. So it is necessary because this condition is not satisfied, this congruence cannot happen. I formulated the theorem here, although it is very simple and immediately follows from our considerations. Just attract your attention, this condition is not in the book. It should be added if b equals 0 is allowed, then this of course happens. A to the 0 is 1 modulo m, because this is simply 1 itself. So one needs to be precise to throw in this extra condition. So back to this sequence, which, as we found, cycles. 1, after a while again 1, after a while again it will be 1, and so further. So the sequence again begins with the same terms. And a natural question here is, what is the length of the cycle, of a cycle? The length of such a cycle is no smaller than phi of m. At most, no bigger than phi of m, at most phi of m. Because we know a to the phi of m is again 1. This may be a full cycle, maybe not. Meaning, this may be a union of many small cycles. So let us distinguish the situation when the length of cycle is phi of m. Let me record the length of a cycle may be phi of m or smaller. When the length of a cycle is phi of m, we say that A is a primitive root modulo m. This is a very important definition. That is how the whole chapter is called, primitive roots. And let me introduce this definition. G, an element of a reduced residue system modulo m, is a primitive root modulo m of phi of m is the smallest. Positive integer say a, call it h, such that g to the h is congruent to 1 modulo m. So for sure, we start with G is an element of a reduced residue system modulo m. For sure, G to the power phi of m is 1 by Euler's theorem. However, there may be a smaller integer h such that G to the power h is congruent to 1 mod m. if we call it here A, not G, we don't know whether A is a primitive root or not. So up to somewhere, and it is already 1 modulo m. Again, here it is also 1 modulo m, but the cycle is shorter. So primitive root means the length of a cycle in this sequence is as big as it is theoretically possible. Namely, the length is phi of m. Phi of m is the smallest positive integer such that g to the power, taken to the power phi of m, is 1 modulo m. Here is an example when the cycle is shorter. Here is an example. You know, we discussed that in exercises to chapter 6, that f m bigger than 6, then phi of m is bigger than 2. We solved the equation phi of m is an integer. We solved the equation phi of m equals 1 and phi of m equals 2. So phi of m is equal to 2 for 3, 4, m. 3, 4, and 6, and never again. From here, we can conclude that m minus 1 is an element of reduced residue system modulo m. M minus 1, I will note that the greatest common divisor of m and m minus 1 is 1. So m minus 1 is an element of reduced residue system modulo m. Why this greatest common divisor is 1? The simplest way to see that is to find the linear combination of these two, which is 1. m minus 1 is equal to 1. Our greatest common divisor is, as you hopefully remember, the smallest possible positive linear combination. The smallest positive linear combination cannot be smaller than 1. In this case, we've got 1. So this is the greatest common divisor. Thus, m minus 1 is an element of reduced residue system modulo m. At the same time, for m bigger than 6, it is not. M minus 1 is not a primitive root. Modulo m. Indeed, what happens when we take powers of m minus 1? M minus 1 squared is m squared minus 2m plus 1, and this is congruent to 1 modulo m. So for this element, m minus 1, the length of our cycle is 2, while as soon as m is bigger than 6, phi of m is bigger than 2. So this element gives us m minus 1, 1, m minus 1, 1. The cycle is too short, phi of m is bigger. So this is not, unless m is too small, this is not a primitive root. Not every element, for sure, that example shows that not every element is a primitive root modulo m. the book at this point uses a different language, and they introduce this definition a little bit differently. I will briefly tell you about the language used in the book. So they introduce definition 7-1 and say FH is the smallest positive integer such that a to the h is congruent to 1 mod m. They say A belongs to the exponent h modulo m. And in this language, they introduce a definition 7-2. So, in this language, for m bigger than 6, or for any m in fact, m minus 1 belongs to the exponent 2, because m minus 1 squared is already 1 mod m. So the smallest positive integer for m minus 1 raised to power h to be 1 is 2. So for m bigger than whatever 3, m minus 1 belongs to the exponent 2 modulo m. That is how the book describes that. How does the book describe it? And after that, they say, what is a primitive root? They say that G is a primitive root modulo m if G belongs to the exponent phi of m modulo m. Oh, you see, this is absolutely the same thing as I did. I just did not introduce this heavy construction. So J is a primitive root means that phi of m in our definition, phi of m is the smallest positive integer such that J to this raised to this power is 1 mod m. They mean exactly the same. H is the smallest positive power belongs, and if H is phi, then J is a primitive root. So my definition is equivalent. I just avoid this construction. I briefly recalled it. We will not need it in this exposition. The construction is needed later in the next section in the proof of theorem 7-6, which I will skip. Anyways, so this was just a remark how the book treats it, so that you can compare our treatment and the book's treatment. The most illuminating property of being a primitive fruit is theorem 7-3. If G is a primitive fruit modulo M, then G squared and so further up to G to the phi to the phi of M is a reduced residue system modulo M. In other words, every element of reduced residue system is congruent modulo M to a power of G. So we can think about reduced residue system as a bunch of various powers of the primitive root. That is a different presentation of the reduced residue system, not just bunch of residue classes. It is, of course, but all residue classes are written uniformly as powers of one residue class, or one number if you want, which is a primitive root modulo M. So if we can choose a primitive root, we have a different and alternative description of reduced residue system, which is much nicer than the previous one. The theorem is not difficult to prove. We'll have exactly phi of M elements, so as there should be in reduced residue system. So for the proof, note that there are exactly phi of M right amount of them they all satisfy that the greatest common divisor of every one of them, whatever J is, and M is 1, simply because we started a primitive root is an element of a reduced residue system in the first place. Remember, we started with the observation that we can multiply elements, we can take powers of element A in reduced residue system, otherwise we fail miserably. So G, a primitive root, is an element of reduced residue system. Thus, G is relatively prime to M, so G shares no prime factors in common with M. Power of G has same prime factors taken into different powers as G has, so shares no prime factors with M. So they're still relatively prime. We have correct number of elements. They all satisfy the prerequisite. Gonna think to check that they are all distinct. They are pairwise distinct. Well, indeed, we assume otherwise. For the sake of contradiction, namely, let us have two integers both among these powers from 1 to phi of m, such that g to the power r is congruent to g to the power s modulo m. That means that m divides the difference, so m divides g to the r minus g to the s. And I will rewrite it as m divides g to the r times g to the r minus s minus 1. Now, I want to recall theorem 2-3, which was quite important. Theorem 2-3 tell us that if A divides BC and the greatest common divisor of A and B is 1, these two imply that A must divide C. Let me write it clearer. A divides C. Now we have M divides a product, and M is relatively prime with G to the R. Greatest common divisor of M and G to the R is 1. As we already discussed, greatest common divisor of any power of G and M, any power of G except 0 and M is 1. So the theorem tells us that this divisibility and this condition must imply, thus, we get that M divides G to the power R minus S minus 1. In other words, we can rewrite it as G to the power R minus S is congruent to 1 mod n. However, we have our first assumption, the most important one: G is a primitive root modulo m. So the smallest positive integer, r minus s, is positive unless r is equal to s, but we exclude this case, we assumed otherwise. So the smallest positive integer such that g taken to this power is 1 is phi of m. That is, what does it mean? G is a primitive root. So phi of m is the smallest positive power to raise g to get a 1 modulo m. So since g is assumed to be a primitive root, modulo m, we must have that r minus s, which is a positive integer, is bigger than phi of m. And that cannot happen for our choice of r and s. This choice. 1 s r phi of m. The difference r minus s is at most phi of m minus 1. Cannot be bigger. So r minus s bigger than phi of m cannot happen. So our assumption led to something which cannot happen, that this contradiction finishes the proof. So we proved theorem 7-3 that if a primitive root modulo m has been chosen, the reduced residue system can be written in this way. Reduced residue system modulo m can be written in this way. All right.